cool, so in this video I just want to talk through a very quick example, hopefully string it all together. Hopefully you've got the idea of what we're doing now, but just to make sure that we do, I've just kind of summarised the core idea of what hypothesis testing actually does in a couple of bullet points down here. So the core idea is we're literally asking what is the probability of obtaining a sample given that this null hypothesis is true. So if you imagine our example, which I did up here, so I said that the mean weight of our chocolate bars should be 100 grams. Okay, that's the hypothesized weight. That's what the manufacturer said to be true. I go out, I collect some sample data, and I literally ask the question, well, what's the probability of obtaining this sample data if this is actually true, if the true mean weight is actually 100 grams? So if I get a sample mean weight of 100.5 grams, what's the probability of getting that if that null hypothesis is true, if that mean weight is actually 100 grams? Okay. And then if that probability is small, so we say smaller than the significance level, so 5% is kind of the cutoff value. Anything less than 5% is we say is significant, okay? Then it is unlikely that H0 is true. So literally all we're doing is we're saying if we get a sample size of this, so if we get our sample data as this, and if this is what we currently accept to be true, then what's the probability of getting this sample? If that probability is small, then we can say, that probably won't be true. Just remember, just because you get a really small probability of like 1%, it doesn't mean that this isn't true, that this null hypothesis isn't true. It just means it's unlikely to be true. Hence why we say we never accept anything. We either reject it or we fail to reject it. Okay, nothing is ever accepted with hypothesis testing. But it's all based around this idea of what probability is doing. So okay, let's talk through an actual example here now. Okay, so let's suppose that I've got some batteries, okay, and I look on the packet of these batteries and it says the mean lifetime of these batteries is 200 hours, okay. Well, I think, I'm not sure it is 200 batteries. Like, I've got my reasons, I've used them in the past perhaps, and perhaps they don't quite work as expected. So I say, right, okay, it's either longer or it's less than. So I say, well, okay, I don't think it is 200 hours. So in other words, my alternative hypothesis is that mu is not equal to 200 grams, okay? So what do? Well, I go out and select a sample of batteries. And obviously I'm not made of money and the shop hasn't got a lot in stock. So I collect 15 batteries, buy 15 batteries, and I find that the mean lifetime of these 15 batteries is 205 hours. Now let's suppose that the sort of manufacturer doesn't tell me what the population standard deviation of these batteries lifetime are. So I just measure the standard deviation from this sample and I find it's 3 hours. Now I want to test at the 5% level of significance whether there is a difference in the mean lifetime of these batteries. In other words, are they actually 200 grams based on this data here? Okay. Now first thing to remember is what type of test am I going to use? Now if you remember with confidence intervals, when we're doing confidence levels, there were two types of test. We either use a t-test or we use a z-test. In actual fact, a t-test was pretty much exactly the same thing as a z-test. It's just as n approaches infinity, a t-test approaches what a z-test is doing. So it works in the same way, like it follows the same curve. It's just a t-test that takes into account if you haven't got enough things in your sample or if you don't know what your true population standard deviation is, okay? So you effectively ask two questions. Number one, you say, well, is the sample size bigger than or equal to 30? If the answer to that question is yes, then you need to test, is the population standard deviation known? Again, if that answer to that question is yes, then you can use a z-test. Otherwise, if the answer to these two questions is no, so any of these two questions is no, then you have to use a t-test. Okay, so always put this in mind. Okay, you need to ask yourself two questions. First of all, is the sample standard deviation, is the sample size bigger than or equal to 30? Then you need to ask the question, do you know what the population standard deviation is? If the answer to any of these two questions is no, okay, then you have to use a t-test. Otherwise, you have to use a z-test. Okay, so let's have a look here. First of all, have we got enough things in our sample? The answer is no. We've not got a sample size which is bigger than or equal to 30. So therefore we have to use a t-test. Equally, we could have done it from the other perspective and we could have said, well, do we know what our population standard deviation is? The answer is no. So therefore we still have to use a t-test. Okay? So we're going to use a t-test. Now you remember that a t-test has this thing called degrees of freedom in there. Now the degrees of freedom is always given for for one thing in your sample, you're not testing a difference, for n minus 1. So in other words, here, our degrees of freedom is going to be 15 minus 1. In other words, it's going to be 14. Okay, so that's our degrees of freedom. Now I can calculate my test statistic. So remember, our test statistic is saying, well, how many standard deviations above or below the stated population mean of 200 will 205 lie based on this sample size? Okay, so you remember the way which you calculate it is going to be, so it's t now instead of z because you're looking at t distribution. So the way which you calculate it is you take your sample mean, which is 205, you take away your true population mean, which is 200, and you divide by your standard error, which in this case is going to be 3 divided by the square root of 15. So if I stick all that in your calculator, you should get, well, it's going to be 5 over 3 divided by the square root of 15, which comes back as 6.5. Okay, so actually let's do 6.45. Okay, 6.45. Okay, good. So based on this evidence here, I can say that my test statistic is 6.45. Now just remember, your test statistic tells you how many standard deviations above or below the mean this mean value should lie. Okay, so you're basically saying that if you have a mean weight of 200 grams, so if that's true, then the chance of you getting that, it's going to lie about 6.5 standard deviations from the mean. Now if you remember, just by looking at your curve, so that's a rubbish curve, but it doesn't matter, okay? You've got 200 lying in the middle. That's what you currently believe to be true. That's your null hypothesis. You then basically say, well, where does 205 lie in relation to 200? It's going to lie way out over here, you happy? Because 6 standard deviations is a long, long way from the mean. Remember, we sort of only consider really 3 standard deviations away from the mean. And that's sort of a relatively low probability. So 6 standard deviations away from the mean is going to be a really, really low probability. But let's do it properly, okay? So let's come up here. Let's look at our alternative hypothesis. This tells us that we should be using a two-tailed test, okay? Because it's a not equal to, so we should be using a two-tailed test. So because it's a two-tailed test, we're going to look down here and we're going to look down here. We say, well, actually, what is the size of that critical region? Well, if you look, our significance level is going to be 5%. Okay, our significance level is going to be 5%, which means that our critical region is going to be split in 2 ways. So that 5% is going to be split equally. So you get 2.5% down here and 2.5% up here. Now, the next thing I'm going to do is find out where that critical value is. In other words, where is the cutoff? How many standard deviations away from the mean does that critical value begin? Okay, and the way which I look at this is I say, have a look, okay. I'm going to look, remember that the t values is given in terms of the probability. Okay, it's given in terms of the probability. So you're going to say, well, okay, 2.5% is either here, or you can use the confidence level, of course, which is going to be 95%, okay. Then you look at degrees of freedom, which is going to be 14, find the intersection of that row and that column. Okay, so 14 is going to intersect at 2.145. That's how many standard deviations above or below the mean the critical region is going to lie. So that's my critical value. I'm basically saying anything beyond 2.1545 standard deviations above or below the mean is significant. Now clearly this is well above that 2.145 units of standard deviation. It's well above that critical value, 6.45, right? That's my test statistic. That's well above 2.145, okay? So therefore I can say that this sample here is significant, okay? This sample here is significant. Okay? In other words, because it lies in the critical region, I reject the null hypothesis. Okay? I reject the null hypothesis in favour of H1, I like, if you want to say it like that. Okay, so I need to put this in context. I need to actually put a little statement at the end which actually helps me put this in context. So here we go. I say since, in fact I haven't calculated the p-value, let me do that. Now clearly a value of about 6 standard deviations doesn't appear on here. Okay, a value of 6 standard deviations doesn't appear on here. So what I'm going to do, in fact let me have a look. Does it appear on here? So what am I looking for? 6.45. So I'm looking for units of standard deviation which are close to 6.45. Okay, so it's going to be somewhere probably about 0.005, so something a little bit beyond that. So it's probably going to be for 14, yeah, it's probably going to be well below 1%, okay? So the p-value is going to be much less than 0.01. Okay, it's going to be less than 1%. So because this probability of obtaining the value is less than 1%, okay, so since the p-value of this sample is less than 1%, which is clearly less than the significance level, then I can say that my sample is significant, okay? So I can reject the null hypothesis. Hence, it is the case based on this sample that the true population mean, that the true mean lifetime of these batteries is not 200 hours. Okay, so it could be greater than, it could be less than. All I know is that it's not equal to 200 hours. So always put this little statement at the end. But the process of which you calculate it is really simple. Okay, you're simply saying, where does this test statistic lie in relation to my critical region? Is it in the critical region or isn't it in the critical region? If it is, it's significant. In other words, you can reject the null hypothesis. If it isn't, you fail to reject it. In other words, the probability of it happening is actually reasonably high. Okay, so the way which you go about it is fairly simple. Okay, it's the same for the t-test as it is for a z-test. The only thing that you need to consider is whether you use a t-test or z-test using this thing.